Welcome to a video on section 3.3, differentiation rules. In this section we will be saving a lot of time really by finding derivatives using these rules. I want you to notice the thing in bold and caps, right? You will need to memorize all of these rules if you want to use them and save that time. The first two that we can talk about from before is that the derivative of a constant function is 0, and that's because if you have a constant function, I'll give you an example, like let's say you have the function f of x is just equal to -2. That would just be a line at -2 that is completely horizontal. And so anytime you pick any point on this line and you think of its derivative, it's perfectly parallel to that, also 0. Okay, second one, the derivative of a linear function. Think of the line y equals mx plus b. If you have a particular line, let's just say it looks something like this, the green line to the right. If you were to pick any point on that line and you were to think about its derivative, the slope of a tangent line would again be parallel to and exactly equal to the slope. So all you have to do is just take the slope. So those are a couple things you can use from memory. Let's take a look at the very big rule in derivatives, and that is the power rule. Here it says let n be an element in the reals. Now that r that you see, that fancy looking r, when you write that, typically just put a double line and then kind of write an r around it. That just means real numbers. So let n be any real number. Then, here's the cool part. The derivative of x to the n power will just be equal to n times x to the n minus 1. If you say that in another way, one way to say it is think of whatever exponent we have here comes out front as a multiplier, and then whatever the exponent was, it's going to be 1 less. So you might say bring the power down, reduce the power by 1. A couple other rules just to introduce here at the beginning is that you can take the derivative of terms fx plus or minus gx individually. You can just take the derivative of f prime separately from the derivative of g. I don't know how I said that, but you can take the derivative of f and g separately and add or subtract them at the end. That's what that's saying. The constant multiple rule says if you have a constant multiple times any function, but you're finding the derivative of that, then you can just leave that constant multiple out as a multiplier and just take the derivative of the function itself. All right, so those are 3 rules we're going to be utilizing here. So here's some examples. For each of the functions below, use derivative rules above to find f prime x. So first thing you might notice is that we have multiple terms. So that means we can, and if we use that sum and difference, we can take them individually, right? A derivative of each term, we'll treat them as separate. So in this first one, we're going to use the power rule. So the power rule says that when we take the derivative, we will take the power, in this case 3, bring it down as a multiple, and then just reduce that power. 3 by 1, it becomes 2. Again, 3 comes down as a multiplier, 3 minus 1 is 2. All right, derivative of the second term, I'm going to keep my sign of minus. The second term, you notice, is just a constant, and so its derivative is 0. And of course, this will best simplify to just 3x squared. That will be my derivative function. Let's look at number 2. Pause the video, try it first. Okay, now maybe that you tried it. Again, we're going to be looking at individual terms. The first one here, notice that we have a constant multiple out front of -2. So we're going to apply the power rule to the x to the 4th, but that -2 is already there as a multiplier. So the -2 will just kind of hang out. And now when I use the power rule on x to the 4th, the 4 will come down and reduce the power by 1. Moving to the next term, that's, you can see it looks very linear, right? But if you want to use the power rule, it still applies. There's an invisible first power there. 5 times bringing the 1 down, all right? And then x goes to the 0. And then this last term is just a constant, and the derivative of any constant is 0. If we clean this up a little bit, you always want to do that, right? We want to multiply these two together. We'll get -8x cubed plus, remember the x to the 0 is just 1, 5. And so that will be our derivative function cleaned up. Okay, now this looks a lot messier and may not look like we have a rule, but if you do a rewrite first, if you rewrite the function using some of the techniques from an algebra course, then you'll be able to apply the rules from above. So the first term, 1 over x cubed, you might remember it can be written in another form as x to the -3 power. So that's just using that, remember that a negative exponent acts as a reciprocal. The next one, you might recall that a square root can be written using a fractional exponent. Inside that radical, there's an x to the 1st power, but then the index is a square root, so it's 2. So that's x. That's the same as x to the 1/2 power plus pi. So notice all I did there, I didn't do a derivative, right? All I did is just rewrote the function so that I can use the rules. So now let's go ahead and find that derivative. On the first term, we can apply the power rule, bring the power down out front as a multiple, and then reduce it by 1. Okay, since we're negative, when we reduce, we're going to go down 1 to -4. Okay, second term. Okay, we're going to bring the power down. This time the power is a fraction, but that's not problematic. Bring the power down as a multiple out front, and again, reduce that power by 1. So be careful with your fractions, of course. 1/2 minus 1 will be a -1/2. And then the last one, not so bad. Pi is actually just a constant, so that's going to act as 0. Many times you might want to use this derivative function. You might want to go on to make this, to use this in a problem. So I often find that if you rewrite this without exponents that are negative or fractional, it's a lot easier to use. So an equivalent version of this, since the x has a -4 power, that's a reciprocal, -3 over x to the 4th. And then we've got several things going on here with this term. Okay, we have like a 1/2. I'm going to do the 1/2. But the x to the -1/2, two things. The negative gives it a reciprocal, and the 1/2 gives it a square root. So it's a reciprocal and down here in the denominator. And so that is a cleaned up version that I think is a lot more usable. All right, why don't you pause the video and try this next one that actually asks you to find the equation of the tangent line, which we've done before at the point where x equals -1. All right, if you took a stab at that, let's see what we need. So the first thing we need is we need an actual full point, and this is where x is -1. So I'm just going to plug that value into the function. All right, computation here. We have 3 times -1 cubed plus 5 times -1 squared minus 4 times -1 plus 3. Let's hope for no computational errors. We have -1 cubed is -1, -1 squared is +1, and then we have a negative times a negative is a positive, and it looks like those 3's will just cancel out, and I get an answer of 9. So that means it goes through the point -1, 9. Good. Now, second thing I need to write an equation of a line is the slope. Since this is the slope of the tangent line, we will need to use the derivative to find that slope. So let's use our newfound powers to find the derivative. It's going to be a lot faster. First term, I'm going to go a little quicker. Constant multiple 3. Bring the power down. There's already a 3 there, so it becomes 3 times 3 is 9. And reduce the power by 1. Same thing on the second term. Bring this power down. There's already a 5 there. 2 times 5 is 10. Reduce the power by 1, invisible 1. And this one, invisible 1 here. Bring the 1 down times the 4. The x is now gone, and then the last term is a constant, so its derivative is 0. All right, but we want that slope where x is -1, so let's go ahead and plug -1 into our derivative function, and we have as follows. All right, -1 squared, +1, minus 10, minus 4. So 9, take away 10. -1 minus 4, I believe, is -5. All right, this is my slope. All right, now I have all the elements I need to write that equation of a line. I don't know if you've already done this, but I like to use the point slope formula. Y minus y1 is equal to m times x minus x1. Again, we have our x1 and y1 from the point, and we have our slope over here already. All right, so let's do that. So we got y minus the y value of 9 equal to m, that's our -5, times x minus our x value of -1. And then cleaning this up, I like to always put it in the y as mx plus b form. Let's see, we're going to think about distributing -5 times x, -5 times really a +1, so that'll be -5. And if you add 9 to each side, you should get -5x plus 4. That would be the equation of the line tangent to g of x at the point where x is -1. Let me show you that on a graph. Okay, so here we are on the Desmos page. You can see a graph of g of x right there. I used Desmos to find g prime of -1. Of course, we did that by hand earlier as -5. Notice the point 1, -9 here on the graph. You can see it right there. And if we take that equation that we found earlier and just graph that, you can see that it makes a beautiful tangent line to the graph right there at that point. Okay, hope that makes sense with what we did algebraically. There's a visual of it. Okay, on to the next page. We want to look at something called the product rule. This one is pretty easy to memorize because it has a pattern to it. And here's what it says. If f and g are differentiable functions and you're doing f of x times g of x and the derivative of that, what you actually get is you get f prime g of x plus fxg prime. Okay, so that's kind of a mouthful. And here's another way to say it is take the derivative of the first function, multiply it just by the second function as is, then add in the first function as is times the derivative of the second function. If you want to memorize a short order form of that, you can think of it as something like, in notation, f prime g plus fg prime might be a little bit faster, but writing the x's makes it look a little more official. So let's take a look at an example. Here we have j of x equals x squared plus 2, that quantity times 3x cubed minus 5x, and we're trying to find the derivative j prime x using the product rule. So it says, then check this result by first finding the product prior to differentiating, and then compare the results. All right, so let's do that. So we're going to use this new product rule that you've never possibly seen before. So using it is, okay, the first function, it's going to be x squared plus 2. We're going to take the derivative of that. That's our f prime of x right there. Derivative of the first function. Let's go ahead and do that. Well, term by term, the derivative of x squared, bring down the power, reduce it by 1 is 2x. The derivative of 2 is a constant, so it's just 0. Okay, and then the rule says just times the second function as is. Don't change it at all. So the second function is the 3x cubed minus 5x. Just leave that as is. All right. And then going on with the formula, plus the first function as is. Okay, plus the first function back to x squared plus 2 as is. Don't change it. Times the derivative of the second function. Now we will differentiate that second function. So we're going to take the derivative of the 3x cubed minus 5x. So let's do that piece by piece. The 3x cubed first. Bring the power down. 3 times a 3 that's already there is 9, but reduce the power by 1. That's the power rule. And then here is this linear looking term. Again, there's an invisible 1. Bring the 1 down, multiply by the 5, reduce the power by 1, and the x is gone. So that is our derivative function. Oh, okay, great. That's all. That's all? Yeah, well, you can clean it up and do more, but that's all for now. Let's take a look at the second part of what I've asked to do this. It says, well, check this by first finding the product before differentiating and then compare the results. So what if we had just taken j of x as it was, x squared plus 2 times 3x cubed minus 5x, but first went ahead and did the distribution. Let's take a look. We have x squared times 3x cubed, that's 3x to the 5th, and the next one minus 5x cubed, and then next one plus 6x cubed. See, I have like terms there, and this times this minus 10x. Well, let's clean that up by combining these two terms in the middle. So it's 3x to the 5th plus x cubed minus 10x. That's my j of x simplified prior to taking the derivative. Then let's take the derivative of that j prime of x. I'm going to use the power rule just a few times here. First one, 5 times the 3 that's already there is 15. Reduce the power by 1. This one, 3. Bring the 3 down. Reduce it by 1. And this last one, minus 10. That's our derivative using that first. Now, you notice that that doesn't seem to look like, of course, what we have over here. But we can just ensure that that's the case by doing the distribution and simplification. Let's go ahead and do that. So if we distribute here, we get 6x to the 4th power. And then 2x times minus 5x minus 10x squared. The second one, we need to do quite a bit more distribution. X squared times 9x squared, 9x to the 4th, and then we have minus 5x squared, and then plus 18x squared, and lastly, minus 10. We have a lot going on there. Let's look for like terms. So again, j prime of x is equal to, it looks like we have two terms with x to the 4th. 6 plus 9 would be 15x to the 4th. We have 3 terms with x squared. We've got negative 10, minus 5, negative 15, plus 18 is positive 3, x squared, and then just this one constant term. So yeah, we have a match. Now, one can argue which was easier there. Well, I mean, arguably the one on the right, the old-fashioned way that we could have done it before, might have been easier, but maybe like the one on the left. So as the powers increase, what you're going to find is that this product rule becomes more and more useful. So why don't you try this one right here and see what you get. Go ahead and pause the video, take a shot at it, use the product rule to find that derivative. Okay, now that you've had a chance to do it, here's what you should have gotten. J prime of x. Let's use the product rule. Derivative of the first, bring the power down, reduce by 1, times leaving the second function alone, don't do anything at all, plus the first function, 2x to the 5th, as is, times the derivative of the second function, term by term. This should have been 8x plus 1. Now, if you distributed and clean that up, you could get a more simplified answer, and I'm just going to leave that to you. All right, let's take a look at the next rule called the quotient rule. It's a little more complex looking than the product rule, but you'll need to memorize this, and you can notice that it looks on the numerator portion similar to the product rule. Notice it says f prime g of x, fx g prime. That's the same as the product rule, but notice there's a subtraction symbol rather than an addition symbol between them. And then the one addition to this is that you're dividing by the function in the denominator, which we're calling g of x squared. By the way, the proof to both of these will exist in the book. There's a nice proof for both the product and the quotient rule. We're simply, on this video, just going to be using them. Okay, so what we need to do is identify what is the numerator function. We'll call that f. The denominator, we'll call it g. And that's pretty easy to do. So in this particular example, we can see that, I'm calling it j of x, j prime of x. To use this formula, the top part will be our f of x. Maybe I'll just write this one out aloud. Our f of x will be 5x squared, and this denominator will be our g of x when we're thinking about the formula. So it may be useful just to find the derivatives ahead of time. First one, bring the 2 down, reduce by 1. And the second one, this is just a linear function, it's just 4. So we're going to be plugging these 2 in for where we see f prime of x and g prime of x. All right, let's go ahead and write out this formula. So starting with the numerator, f prime x times g of x. F prime of x we found to be 10x times g of x originally. All right, and then minus fx g prime x. fx, the original, 5x squared, times g prime of x we found to be just 4, all over, the formula says g of x squared. That's 4x plus 3 quantity squared. There you go. That is your derivative function. Often, again, it's very useful to clean this up algebraically so that you have it as simplified as possible. So let me go ahead and take a couple extra algebra steps with you here. All right, so let's distribute this 10x. We're going to get 40x squared plus 30x minus these two multiply together, 20x squared. And the denominator, you can distribute that, but I'll just say in general it usually doesn't pay off. Because if there's any simplification to do, it's best to leave it in factored form. So let's see, we have two x squared terms on the top. So we're getting 20x squared plus 30x. You might look briefly to see if you can simplify more by factoring in the numerator. And what I notice is they both have a 10 and they both have an x. And if you were to factor that out, it would be something like 2x plus 3. That doesn't look like it'll simplify with anything on the bottom. So that's probably our best simplified answer for our derivative function. All right, looking on to this next one, I'm asking you to use the product rule, but I'm lying to you. That's a typo, guys. All right, fix that. Please use the quotient rule, all right, to obtain the derivative of k of x. And there it is off to the right. So try to use that same formula, identifying this is f and this is g, and then find your f prime and g prime. And go ahead and pause the video and try that. All right, and here is my work. Hopefully you've had a chance to try that yourself. I have it simplified all the way down to negative 13 over 4x minus 3 squared. Okay, let's move along to the next page. On this page, I'm talking a little bit about choosing a technique. You notice that we have these new rules, the power rule that we've now added, the product rule and the quotient rule. You might think about what will work best for each. So like on this first one, for example, you might notice, hey, it's a function times a function, and maybe I use the product rule. Me, myself, probably I would not. I would probably actually just distribute this first because it's very fast and easy to do. Something like 2x squared. You got 10x minus 2x is 8x, and then negative 2 times 5, negative 10, and then just take my derivative pretty quickly as 4x plus 8. I found that to be the easiest. I don't feel like I need to use the product rule. I can just distribute that out. And also, like for the second one here, you know, it looks like I could use the quotient rule. And the quotient rule is the one we just went over. But I also noticed that this term in the denominator seems to kind of nicely cancel with each one of these. And so maybe another way to do it would just be rewrite it prior to taking the derivative and just use the power rule 3 times. So again, you might think of it as like, okay, well, what is x to the 5th divided by 2x cubed? I'll write this off to the side, but I'm going to do the other terms in my head. If you think about x to the 5th, oh, I said 2x cubed over 2x squared, you'll notice that the exponent of 5 minus 2 will give you x cubed, and so you can just rewrite that as 1/2 x cubed. So I might just rewrite this as 1/2 x cubed the next term would be 5 halves x, because x cubed and x squared cancel to x. And then the last one minus 3 halves and x squared divided by x squared. That's this term. Will just go away. And then I can just use the power rule, bring the 3 down, reduce it by 1, and then there's my answer pretty quickly with the power rule. And the same thing for this last one. If you rewrote it as 3x cubed minus x plus 5, but then you thought about this denominator as x to the half power, you could just basically divide each one of these by x to the half power and make this cleaned up a little bit first, and then you could just use the power rule. Now remember, when you divide things with the same base, you can just subtract the exponents. So 3 take away a half would be 5 halves, and you can work that out. And then the second term, this is an invisible x to the first. 1 minus the denominator of 1/2 would be 1/2. And then the last one, there's no x in the numerator, so you're just using a negative exponent to write that. Then you could find your derivative just using the power rule, which I won't do, but just noticing that there's other ways to do these rather than always using the product and quotient rule. So even though those are nice rules, you might want to think about when it's best to use and when it's not best to use. Here's an application of the product and quotient rule using just a table. You can see I don't quite have enough space between those two, but anyway, let's just go with it. We're going to use this information off to the right on this table here. Notice it has values for x, 1, 2, 3, f of x, and f prime of x at those given x values. So this is given the tables at the right, and that h of x is equal to 3x cubed h of x. I don't think that's correct. Let's fix that right there. All right, that's going to just have a little alteration. What I meant to write in there is f of x, so change that to f of x, and g of x is f of x over 4x to the fourth. Find the following. So the first one is h prime of 2. So the first thing we're going to do is we're going to find h prime of x. And so notice I had to modify this up here. So what rule we're going to use is going to be a product rule, and that's because it's really 3x cubed. There's an invisible multiplication time f of x. So the product rule says the derivative of the first, what's the derivative of 3x cubed? Bring the 3 down, reduce by 1, times the second as is, plus the first as is, times the derivative of the second. In this case, we don't know what fx is, so we'll just write f prime of x. That's h prime of x. If we want h prime of 2, we'll just simply plug in 2. So 2 goes here, and then 2 goes here, all the way throughout this expression. Everywhere I see an x, I'm replacing it with 2. Now you might be worried a little bit about what in the world's going on with f of 2 and f prime of 2, but notice over here, when x is 2, f of 2 is 0, f prime of 2 is 1 given in the table. So I'm just going to insert those values and evaluate as I go. Let's see. 9 times 4, 36, times f of 2. F of 2 would be 0. That's going to be easy. I like that. Here we have 2 cubed is 8 times 3, 24. And then f prime of 2 will be this bottom value of 1. And so we're just going to get 0 plus 24, or 24 for the first one. Why don't you pause the video and try finding h prime of 3. All right, now that you tried that, you maybe recognize you just need to plug 3 into the same thing. So we have 9 times 3 squared times f of 3 plus 3 times 3 cubed times f prime of 3. And so we should get 9 times 9, 81. F of 3 is negative 3. So the numbers are getting a little larger here. Plus 3 cubed, 27 times 3, 81 times f prime of 3, negative 5. So we've got to evaluate what these values are. All right, so I have a negative 243 plus a negative 405, which I believe gives me a negative 648 if I didn't make any computational errors. All right, I'm going to leave g prime of 1 for you. You can ask me about that later if we have a different answer. Go ahead and try it now. All right, you may pause the video and see what I did. Notice that I used the quotient rule on g of x and then plugged in down here and evaluated final answer of negative 1, assuming no errors there. All right, let's proceed to this page here on higher order derivatives. It says the derivative of a function itself is a function. We already knew that. So we can also find the derivative of a derivative. That's interesting. The new function obtained by differentiating the derivative is called the second derivative, all right, meaning we've taken the derivative of the original function twice. Furthermore, we can continue to do that for third derivative, fourth derivative, and so on as far as we need to. So these all together are called higher order derivatives, and here is the notation for that in the table. So you can see that if we have a function f of x, that we will call the derivative f prime of x, second derivative f double prime of x, f triple prime of x. Eventually we'll just put an index up there. So for example, if I wanted the seventh derivative, I would do something like that. You don't have to put the parentheses up there if you don't want to, but I usually do. The other form for this would be if you have a function that you're just calling y, you can do y prime, y double prime, y triple prime, and so on. Notice I put just don't for the nth derivative, like it's just a mess. And so I like to just go back to this notation if needs be, or use the notation at the right. Other alternative notation for y, you can use dy dx, that's rise over run, or change in y over change in x. D squared y over dx squared. We can talk more in class about why you put the square on the d and on the x rather than at the end of the y. D cubed y over dx squared, dny over dxn for any higher order derivative. All right, great. So let's take a look at how to find those using those shortcuts that we've been given. If g of t is this, find g prime of t and g double prime of t. Let's use the power rule. G prime of t, first term, bring the power down, reduce by 1. Second term, bring the power down, reduce by 1. Third term, bring the power down, reduce by 1. So for the second derivative, all you're going to do is look back at the first derivative. You're not going back to the original function. And so we're going to do a term at a time. First term, bring the power down, 12 times 2, reduced by 1. And the second term, bring the power down, reduced by 1. And the third term is a constant, so it's just 0. That's my second derivative right there. And you could just similarly find third derivative, fourth derivative. All right, so here's a few for you to play with. This is a 7th degree polynomial. It says find the following. What is the 5th derivative? What is the 6th derivative? 7th derivative? 8th derivative? And then a challenge of the 12th derivative. Why don't you pause the video and try those? I hope you notice that as you begin to take the derivatives, the terms begin to kind of drop out left to right. We get rid of this one first, then that one goes on the second derivative, then that one goes a few derivatives later. And so at the end, you're only really dealing with two terms. By the time you get to the 5th derivative, I have 2520x squared plus 600. All right, in other words, this 5th power here, since I've taken 5 derivatives, is all the way down to 0 power, and it's in essence 5 times 4 and times 3 times all that, so on. So as we take the 6th derivative, we're going to notice we're just get down to one term. We're going to take that 2520x squared, bring the power down, which is a 2, multiply it, you get 5040x, and then this term drops out to be a 0. Take the derivative one more time, it's just 5040. Take the derivative one more time, it's 0. And you might just imagine taking the derivative of 0 infinitely many more times. It's always going to remain 0, so the 12th derivative would be 0. All right, let's take a look at finding specific tangent line. So here we're asked to consider the function f of x is 2x cubed minus 54x. Where is the slope of the tangent line negative 54? So the slope of the tangent line, that's our derivative. We're going to start by finding that using our newfound rule. Bring the power down, reduce it by 1. That's just the linear term minus 54. We want to know where this derivative function is equal to negative 54. So we're going to be solving where 6x squared minus 54, the derivative function, equals negative 54. All right, so that's in essence saying where is f prime of x equal to negative 54? Is there a point on the graph where the slope of the tangent line is negative 54? Well, if we add 54 to both sides, you can see that this is going to solve out really nicely. 6x squared is 0. Cut to the chase, x equals 0. So that's the answer of where is the slope of the tangent line. Negative 54 is when x is 0. All right, looking at this last one, where is the tangent line horizontal? Now that's another way of saying where is the derivative equal to 0. When we have a slope of 0, right, that would be a perfectly horizontal line. Slope is 0. So it's just code for that. So I'm going to solve where the derivative is equal to 0. The derivative is 6x squared minus 54. Where is that equal to 0? If we add 54 to both sides, and then we divide by 6, we can see that it's at plus or minus 3. Remember, when you take that square, you got to add that plus or minus. So it should be on the graph at 2 places. That's all for this video. Hope that that helped out, and we'll see you in class.